Welcome fellow chemists to the 10th video in the alkene reaction series. Unlike all previous 9 videos, this is radical substitution and there is still an alkene left when the reaction is finished. How and why there is still an alkene after this reaction occurs is mentioned in my video on question 58, which was part of the 2019 US National Chemistry Olympiad. Although the reaction is a different class, knowing what happens and why requires a solid understanding of the radicals. Out of the most common ones we've seen so far, the tertiary radical is the most stable, but the lone electron in all 4 on the screen is kind of stuck where it is. However, this is not true for all radicals, and this is why allylic and benzylic radicals are more stable. Unlike the other 4, the electrons in these 2 are delocalized, meaning they can move around and form new structures. You've heard this concept before with the term resonance. Allylic radicals can form 1 new structure. Counting the original, this gives it 2 contributing resonance structures. Even though the electron is on a primary carbon in both, the resonance results in added stability, which is why the allylic radical is more stable than tertiary. The benzylic radical, with its large benzene ring, can form even more structures. Based on how things can be drawn in 2 dimensions, we would get 5 unique structures, though you can scream and yell that it's actually 4 if you'd like. Regardless, this makes it more stable than tertiary, and you would think it must be significantly more stable than allylic, but if you noticed before, it was approximately equal. I could not find a satisfying answer to whether one is definitely more stable than the other, but if you're interested in some discussion on the topic, then check out the link in the description. Knowledge of these radicals allows us to predict potential products without going through the entire mechanism. In fact, this reaction from the beginning of the video was an example of the substitution we want to happen. However, you may know that bromine is capable of adding to the double bond, forming a dihalide product in the process. This means limiting the amount of bromine molecules used would help reduce the amount of unwanted dihalide product, but that isn't all. You may also know that hydrogen bromide, the product of the substitution we want to happen, is also capable of reacting with the double bond, giving us the following. So reducing the amount of HBr produced is also needed to avoid unwanted products. To avoid these side reactions, what we need is some clever chemistry. To accomplish this goal, N-bromosuccinimide, or NBS, is used. Like with other radical reactions, lighter heat along with peroxide initiates a reaction which generates a bromine radical. This radical removes the allylic hydrogen, which results in HBr and an allylic radical. The HBr is in such small quantities that it does not add to the double bond. Interestingly, another NBS reacts not with the allylic radical but with the HBr instead. This forms bromine molecules. The bromine molecules are also not produced in significant quantities to add to the double bond. When bromine molecules react with the allylic radical, the allyl bromide product is formed as well as another bromine radical. This bromine radical allows the reaction to continue or propagate in the same manner, resulting in more allyl bromide. So thanks to the low quantities of HBr and bromine formed during the reaction, we don't have to worry about side products. However, we do have to be aware of the structures of resonance contributors. Let's look at the reaction involving propanene. After the allylic hydrogen is removed, we get the radical we care about and HBr which we don't. We can make the other resonance contributor, which looks suspiciously like the first. Confirming our suspicions requires reacting each with bromine and looking at the product. They look very similar again, and if we name them, we find both molecules receive the same name and thus are indeed the same product. But what about hex 3-ene? If the hydrogen removed comes from the second carbon, it is the same as if it came from the fifth. So there is only one initial allylic radical and the HBr, which again we will ignore. When we look at the resonance contributors, they look quite different. We can confirm if they actually are different by reacting each with bromine. They look like 2 different products, and indeed we find out this is the case as we get 2 different names. In both propanene and hex 3-ene, only one initial allylic radical can form, but that's not the case for pent 2-ene. Pause the video and try to determine the major product or products in this reaction. There are 2 allylic positions on this molecule, but that doesn't make them equal. The one on the left is a primary position, and on the right is secondary. If you're thinking it would be unlikely that the radical forms in the primary position, it is a very good thought indeed, especially considering how selective bromine radicals are. Now when we look more closely at that secondary allylic radical, we find its resonance contributor is exactly the same. After the bromine finally lands on the molecule, it forms one product, 4-bromo-pent-2-ene. To briefly summarize what has been covered, allylic and benzylic radicals are more stable than tertiary. N-bromosuccinimide is used to add bromine to the allylic position as it reduces unwanted side reactions. The resonance contributors of the allylic radical affect product distribution. If they are identical, only one product forms. If they are different, 2 products form. If there are 2 different initial allylic radicals that can form, bromine will selectively produce the most stable one possible. Then you must consider the resonance contributors to determine the expected product or products. And that concludes my 10th alkene reaction video. So thank you very much for watching. If you have an idea for another video or series that I should make, leave a suggestion in the comments.